Hello everyone, welcome to my video. In this video, we'll talk about example 5/17 from lecture 21. First, let's read this together here. The motor A, the smaller one, accelerates uniformly from 0 to 3,600 revolution per minute in 8 seconds after it was turned on at time t equals 0 from rest. It drives a fan which is attached to drum B. The effective pulley radii are shown in the figure, which is right here. Determine the number of revolutions turned by the drum B during the 8-second startup period. That's number one. And part B, the angular velocity of drum B at 4 seconds and the number of revolutions turned by drum B during the first 4 seconds of motion, assuming no belt slip. Okay, so the belt is connecting two objects tightly. There's no slip going on. That means how much the belt goes, that means how much the wheel or the drum or the motor goes. So after thinking about this for a moment, let's start with what's given to us. Based on the question, we have this whole thing happened for 8 seconds, right? From 0 to 8 seconds, accelerate from rest to 3,600 revolution per minute. So we'll call this state number 1 and state number 2. Okay, state 1, we'll say this is a state at rest, and state 2 is t equal to 8 seconds. We're just referring to 1 and 2, state 1 and state 2 throughout the whole scenario for our terms. So our angular velocity or omega of this motor when it at 8 seconds is 3,600 revolution per minute. First off, a revolution per minute is not our standard unit. We need to convert it into radius per minute. One revolution means one full circle. In radians, that means one full 2 pi or 360 degrees, but we don't need degrees, we want radians. So one revolution means one circle, 2 pi. So we have 3,600 circles, 2 pi's, per 60 seconds. So we'll do the conversion here. 376.99 radians per second. This should be our first step. Then let's take a look here. What do we want? We want the number of revolutions turned by drum A during the 8-second startup period. So that means how many circles does it go? Right? If you recall from the lecture slides, how many circles does it go? This is essentially in a curvilinear motion or linear motion. This is essentially the displacement, but just measured in terms of angles. So part A is essentially asking the total angular displacement. Right? Displacement is a keyword here. Let me jump part B and talk about part C here. Part C is the number of revolutions turned by the drum B during the first 4 seconds. Still, this is a total angular displacement we want to find. That's for part A and part B, part A and part C. And part B, the angular velocity of drum B at t equal to 4 seconds. What is this? Okay, think about 3 parameters: displacement, velocity, acceleration. Which one is this? This is the angular velocity, right? So we're given time, we're given angular velocity of A. So we'll need to use this to find out what is the acceleration of A, what is the angular velocity of B, what is the angular acceleration of B, right? We'll use this as a starting point, the relationships that we know. And we also know A and B they are connected. If A and B are connected with the same belt, or essentially they are touching, what does it mean? Okay, while I'm writing this down, you can think about it for a moment. We know A and B are connected. Hopefully you can figure it out now. If A and B are connected, that means the velocity is going to be the same. Right? Because how much the belt goes, that's how much A goes and how much B goes. Right? They're connected. They are connected with the same belt without slipping. So the velocity or tangential velocity is the same. Well, so far you should remember that in angular motion or in rotation, there is only tangential velocity. There is no normal velocity. There is normal acceleration, but there is no normal velocity. So whenever we're talking about velocity, that is a tangential velocity. VA and VB are the same. And that means we're talking about tangential. The tangential acceleration of A will also be the same of the tangential acceleration of B. Because they are on the same belt, so whatever is pulling them, being pulled together. They're getting the same acceleration for A and B. Okay, with that in mind, let's see. We're given the angular velocity of A at 8 seconds. Okay, this is state number 2. Oh, just raise it. State number 2. Let's find out what is the angular velocity of B when t equals 8 seconds. We can use the relationship we just got because VA and VB are the same. Angular velocity or tangential velocity is R omega. So we have RA omega A2 equals to RB omega B2. Now rearrange a little bit. Omega, angular velocity of B when t equals 8 seconds, can be calculated by the ratio of RA over RB times omega A2. Okay, subbing the number here, 75 over 200. Okay, you don't really need to do the conversion. You can do the conversion, but because we're doing a ratio RA over RB, the millimeter will cancel out. So it doesn't really matter if you do the conversion or not. But it's always helpful to think about it for a moment. Do you really need the conversion since this is not the standard unit? In this case, we don't need it. 1 for 1.37 radius per second. This is the angular velocity of B when t equals to 8 seconds. And this is given by the ratio of A and B, the radius. Okay, so now we have angular velocity of B. What about angular acceleration? Well, in order to find the angular acceleration of B, apparently in this case we also need the angular acceleration of A. Well, we know the angular speed or angular velocity of A already. Let's use this to find our angular acceleration of A. Angular velocity of A is equal to, by equation, is angular acceleration of A times time. Right, this is essentially V equals to AT, right? Velocity equals to acceleration times time. In rotational motions, this is our velocity, this is our acceleration. So we have angular velocity, angular acceleration. The time is the same thing. So our angular acceleration of A is given by 99, which is we calculate here, divided by 8 seconds. So it takes 8 seconds for the motor to accelerate from 0 to 376.99 radius per second. So that's our angular acceleration. In this case, 47.12 radius per second square. Okay. Angular acceleration. We used this relationship to find the angular velocity of B. Now we can use this relationship to find the angular acceleration of B, right? So, because we also have tangential acceleration of A equals to tangential acceleration of B, and that means acceleration is r alpha, the radius times angular acceleration. It's given by the equation here, alpha A, rb, alpha B. In this case, we are having uniformly, accelerates uniform. That means alpha A and alpha B will remain the same throughout the process. We don't need to worry about the varying angular acceleration. So similarly, we'll rearrange a little bit to find out our angular acceleration of B is, again, given by the ratio between RA over RB times alpha of A. Subbing the number, 75 over 200 times 47.12 equals to 17.67 radius per second square. How fast B is accelerating? 17.67. Now, let's go back to A, B, and C. A is asking, what's the total? The exact word is the number of revolutions turned by drum B during the 8-second startup period. And we explained at the beginning, that's the total angular displacement. So displacement, connecting to the equations we have for linear motion, we can have the total angle that B rotated, which is displacement, will be theta 0, the initial displacement, plus velocity times time, which is the theta dot B times time, plus 1/2 alpha B t squared. If you think about this, this is essentially as displacement is s naught plus v naught t plus 1/2 a t squared, right? Comparing with our linear motion equations, kinematic equations that we have before. So now in this case, both of them are 0. We have 1/2 times 17.67 times 8 squared. 565.44 radius, and we'll divide this by 2 pi to get 90 revolutions or rotated for 8 seconds. Okay, this is our part A. And just quick note on this, why they are 0? Well, because we start from rest. That means you don't have angular displacement at the beginning, and you don't have any angular velocity at the beginning because you start from rest. You start from 0. So you only have this part. Okay, part B, we want the angular velocity of drum B at time t equal to 4 seconds. So we want the velocity at 4 seconds. We have acceleration, so we'll just get B at t equal to 4 seconds. Velocity is acceleration times time. T equal to 4 seconds. 17.67 times 4 equals to 70.68 radius per second. This is our angular velocity of B at 4 seconds. Part B. Part C is the number of revolutions turned by drum B during the first 4 seconds. Again, so similar to what we have for part A. So theta b, the total angular displacement at 4 seconds. Again, we start from 0, so both terms are still 0. We just have this term, 1/2 alpha, the acceleration, t at 4 seconds. In this case, we're subbing t equal to 4. 4 squared. 141.36 radian, and convert this into revolution because you're asked to calculate how many revolutions. 22.5 revolution. That's our answer. Okay, I just want to finally point out, just remind you, this is velocity is acceleration times time, and this is total displacement, s naught plus v naught 0 plus 1/2 at squared. I just want to see how similar are they comparing the angular motions versus straight line motions. Thanks for watching. I'll see you next time.